All right, so now moving through electromagnetic theory. We discussed Maxwell's model earlier, and that's the electromagnetic wave. And I drew that before I started the video so that you couldn't make fun of me and give me a hard time, because I suffered through and it took me a couple times to draw that. So that's the electromagnetic wave, and it's an oscillation between our magnetic and electric field. Okay, it's perpetuating, and it doesn't require a vacuum. So there are 5 properties associated with electromagnetic waves, and that's our focus over the next little bit here. So the first one, electromagnetic waves are comprised of oscillating electric and magnetic fields. You already knew that, okay? That hasn't changed. So it's more of a going into a more formalized definition of electromagnetic waves. The electric and magnetic fields are perpendicular to each other, and we all know that because we all suffered through trying to draw these 2 waves perpendicular to each other. Me more so than the people that have any artistic talent, since I lack a bit. The vibration of the electric and magnetic fields are perpendicular to the direction of travel of the wave. So it's very much a transverse wave. So it vibrates perpendicular to the direction the wave is traveling. Okay, so I'll put that in brackets. It's just saying it's a transverse wave. Fancy speak for that statement right there. 4, the electric and magnetic fields vary sinusoidally in phase with each other. So that's basically just describing what we have drawn above. Okay, the two waves are in phase with each other, and they generate each other as drawn. So let's just put under there, see drawing above. See drawing above. And finally, electromagnetic waves travel at c, the speed of light in a vacuum. Now, on an earlier page, I had v equals. What we're going to have is our notation up here. Let's just put it up here. So the velocity, VL, velocity of light, 3 times 10 to the 8th meters per second. We use small c to indicate that. Okay, so you're going to see in textbook c equals 3 times 10 to the 8th meters per second. So that's a constant you want to add to your sheet. Make sure you have it for test purposes. So none of those 5, probably if I said come up with 5 properties without showing you this slide of the electromagnetic wave, you should have been, or you probably would have came up with that one we talked about earlier. That one you could have come up with, but that was, we were reviewing transverse waves. You would have told me they're sinusoidal. And some of you might be able to told me the 5th one. So there's not anything that's new or shocking. It's basically formalizing those properties. So let's talk about the speed of light for a second. Electromagnetic waves are still governed by the universal wave equation. So what does that mean? V equals F lambda. So we're back to adding that formula to our formula sheet. It comes forward. It's nice when things are uniform because you don't have to memorize or learn new formulas. Now, the electromagnetic spectrum. So what I've tried to set up in the note, and as you'll see, doesn't work out perfect, is I tried to kind of categorize certain regions in our spectrum. So I'm just going to put some black dashed lines to separate them. And what I have below is kind of the descriptor or something that's of equivalent size. So radio waves are roughly or approximately the size of buildings. Okay, microwaves are about the period between the crests is about the distance of a grain of sugar. Infrared, single-celled organism. Visible light, it's about the size of a bacteria. Okay, the size of a bacteria. That's our lambda. We're talking about our wavelength here. Ultraviolet is our molecules. X-rays have a wavelength about the width of an atom. And gamma rays, excuse me, are about the width of an atomic nuclei. So this is the region, the visible light that we can see. So here's my attempt to help kind of visualize as it decreases in wavelength. So the radio waves come in like this, and then our microwaves, infrared, visible, ultraviolet, X-ray, and gamma. And that turned out so much worse than it did in my head, but in my head it looks perfect. So let's use our imaginations here and pretend I did a great job, and you can compliment me on that tomorrow. So what are we looking at for an approximate wavelength here? So lambda, within our visible spectrum, approximately 4 times 10 to the negative 7 meters. I'll put lambda visible to 8 times 10 to the negative 7. All right, so that's approximately the lambda for light waves that we can see. All right. So we can, electromagnetic waves allow information to be encoded, and you're probably familiar with one more than the other. Back in the good old days when I used to listen to some good old country on the only channel we got in the truck, it was AM. And that is amplitude modulation is what that means, that AM. So that means the information that was encoded by the music was based on the amplitude changes in the wave that was sent out and received. Now FM deals with, or means, frequency modulation. So because there's more range in terms of frequency than there was in amplitude, more information could be encoded. All right, so more information could be encoded, and it allowed for some nice features like stereo. So that when I started listening, getting FM, trying to figure out why one speaker wasn't working and the other one was, and then both were sometimes, until I figured out, hey, that's what stereo is, right on. All right. So as we move through, we now have kinematics formulas for uniform velocity, because waves don't accelerate and they don't accelerate, they don't speed up, they don't slow down. So uniform motion from our kinematics, delta D equals V delta T. If we make the following substitutions, so we're going to take or assume that lambda is our delta D, the length of one wavelength. Our period and delta T go together. That is where our universal wave equation comes from. So just as a quick reminder, delta T, so we replace delta D with lambda, B remains the same, delta T becomes that. We've talked about, or you'll recall that period, 1 over the frequency, isolating, multiplying both sides by F. That's where our universal wave equation came from. Okay, so already shown in the grade 11. And down here below, the speed of light is a constant for all electromagnetic waves. Okay, so C equals, I want to move that over, C equals 3 times 10 to the 8th meters per second. There we go, and that is for a vacuum, so in a vacuum. All right, a quick example then. If the radius of the Earth is 6.4 times 10 to the 6th, compare the travel time if you were in a car traveling at the speed of light, which would be kind of cool, versus a car traveling at an average speed of 100 kilometers an hour. So, information R equals 6.4 times 10 to the 6th meters. We know the speed of light, 3 times 10 to the 8th meters per second. Our velocity of the car, 100 kilometers an hour, which translates to, let's call it 27.8 meters per second. And for those that don't remember, circumference is 2 pi r. All right, so 2 pi times 6.4 times 10 to the 6th. So let's go with approximately 4 times 10 to the 7th meters is the circumference of the planet. So part one at the speed of light. So that would be pretty cool. Oops, delta V equals VT. So we have the 4 times 10 to the 7th equals 3 times 10 to the 8th times time. So when we divide that out, we find that it will take you 0.13 seconds to go around the circumference of the planet. All right, so if you got in that car and you were able to go that fast, which was really neat, you wouldn't have to worry about getting speeding tickets. No one would catch you. Steering, another problem. If you got a car that goes that fast, that's the least of your worries probably. Now, what happens if we slow down? What happens if we were at 100 kilometers an hour? So just so you can see how significantly different it is, 4 times 10 to the 7th equals 27.8 delta T. So our time turns out to be 1.4 times 10 to the 6th seconds, which translates to approximately 400 hours. All right, so that speed of light is so fast, virtually instantaneous to the eye. And we talked about, when we talked about lightning and thunder, the lightning, that lightning bolt, you see it virtually instantaneous. There's a delay because sound is significantly slower than the light, and that's why that thunder comes in after you see the lightning bolt. So, second example, it's 1.49 times 10 to the 11th meters from the Earth to the Sun, so the distance from Sun to Earth. How long does it take light from the Sun to reach the Earth? Well, we know delta D equals V delta T. So we have 1.49 times 10 to the 11th equals 3 times 10 to the 8th delta T. So when you calculate that in seconds, we get 496.7 seconds, which is 8 minutes and 17 seconds. So when you are looking at light coming from the sun, it's actually not the light that was just generated, it's 8-minute-old light, which still works the same. New light, old light, same thing. But think of it this way, if you were looking through a telescope, here's my telescope, okay, I have to write what it is just in case, and you are looking at faraway stars, the way you see objects is when the light enters your eye. So you're actually looking at light with a time lag. So you're looking at galaxies that in some instances the light could be hundreds of hours old, years old. It depends on what objects you're focusing on. But technically, a planet, if you're looking at a planet or a star in another galaxy, it could have been destroyed and you won't know it for several years because it takes that long for the light to reach us. Similarly, in a worst catastrophic approach, if we look at our sun, it'll be 8 minutes before we realize the sun has actually been blown up or destroyed or stolen or whatever happens in the future. But it'll be an 8-minute delay before we're aware of the catastrophe. So even though light is very, very fast, travels at high speed, there's still an immense amount of distance that needs to be traveled when we're talking about the solar system. So when they're looking at these faraway planets with these telescopes, they are looking at it through a time phase, or they're looking at it in terms of a delayed frame of reference. All right, so we are continuing to move through this kind of introductory note on our light topic or light wave topic.